What are you working on, Brownie?
I'm just working on some linear algebra homework. Do you think you can explain how to find the derivative matrix given a basis of functions?
You got it. Hello, everybody. Today I'm going to be talking about the matrix representation for the derivative operator. So what you might see in a problem is they'll give you some functions representing the basis for some vector space of functions, and what you need to do is find a matrix representing the derivative transformation in that vector space. So let's talk about how we can represent those respective basis functions in their vector form. So 1, 0, 0, 0 is going to correspond to 1, 0, 1, 0, 0 is x, 0, 0, 1, 0 corresponds to x squared, 0, 0, 0, 1 corresponds to x cubed. And so let's say we have the polynomial 3 minus 5x plus 11x squared plus 3x cubed. If we wanted to find the vector representation of that, we could go ahead and expand out the linear combination of the basis vectors and sum all of those up, and what we get is 3, negative 5, 11, 3. So each row corresponds to the different coefficient in front of the respective powers of x. And you can go back and forth between, the function representation and the vector representation. Some other functions with their respective vector representations. So negative 3 plus 4x squared is negative 3, 0, 4, 0. X squared plus 7x cubed is 0, 0, 1, 7. Just 5 would be 5, 0, 0, 0. And you're not really limited to these like tiny numbers that I'm using up here. You can go ahead and use any real numbers or even complex numbers for that matter. So let's talk about how we would find the derivative of this function. Traditionally, what you would normally do is probably use the power rule, and the whole reason why we are allowed to find some matrix representation for the derivative in this vector space is because the derivative is in fact a linear operator. What that means is it obeys vector addition, which means I can individually take these derivatives, and it obeys scalar multiplication. So let's say I'm just taking the derivative of negative 5x. What I could do is take the derivative of x first and then multiply negative 5 to that. And so if we go ahead and take the derivative of this polynomial, this is the result that we'll get. But what we're interested in is some matrix A, where if we multiply our vector representation of some polynomial, that output vector is the vector representation of the derivative of that original polynomial. And to do that, we actually only really need to know how the basis vectors get transformed. So I went ahead and took the derivatives of all of our basis vectors, and over here I put how each respective basis vector gets transformed. So check that. Now we're actually done with the problem here. We found our matrix because all we need to do is collect these respective output vectors, and those are going to be the respective columns of our matrix A. So if I do that, and I arrange the columns respectively, this is our matrix A, and we can go ahead and check with some specific vectors that this does indeed do the derivative transformation. Let's try that with our original vector. So A times that original vector, take this column, dot it with this row, it's going to result in negative 5. Take this column, dot it with this row, second component of that output vector is going to be 22. Column, dot with this row, it's going to be 9. Column, dot with that row, 0. And you can go ahead and check this in a calculator if you don't trust my math, but in general, what you'll notice is for bigger vector spaces, specifically for polynomials, there's going to be a pattern in this matrix. So as you see, as you have bigger and bigger vector spaces, it's going to be a 1, 2, 3. For later, it's going to be a 4, 5, so on and so forth. So this output vector does indeed correspond with the derivative of this function. And you can see that negative 5, 22, 9, negative 5 plus 22x plus 9x squared. So with that in mind, that's all I have to cover for this. If you have any specific other topics that you want me to cover, please let me know and I'll go ahead and do that.